This meeting is being recorded.
Welcome back to class. So today is electronics design. Excuse me. And as a reminder, we're doing the experiment of flipping the order. So it used to be previous unit, you made a board. This week you designed it, and then the following unit you programmed it. Now you've all programmed existing development boards. This week you're going to design a development board, and then in 2 weeks you're going to make it. No recitation in the coming week, and next week we're back in labs to do large format machining. This is where you make furniture size things. So, assignment. At the end, I'll talk about test equipment. The group assignment, it will be to use that. But the individual assignment is you're going to design a development board to interact and communicate with an embedded microcontroller. Embedded means you design the processor into your board. You're not going to make a daughter board that goes on something else. So a good example for this week is Adrian, who's done a series of these. So here's the Adrianino, which is a development board for one of the AVR processors. Then he went on and did a development board for one of the ARM processors. And most recently, he did one for one of the Xiao processors. And this shows part of why we like the Xiaos so much. You can use them as a complete board by themselves. But what his board does is it breaks out a button to interact with it, an external LED you can blink, and then some connectors to connect to other sorts of inputs and outputs that we'll be talking about. So those are Adrian's examples, but I also have linked a few other ones. So this week can be not just technically, but artistically creative. So Annie, when she did this assignment, decided to make me as her board. And this was a fun one. Jan made this cat as the board. So, engineers typically make just, rectangular boards or boards that fit a case, but you don't have to. The board itself can be part of the expression of the week. So lots to cover. Excuse me, 2 parts to the class. The first part is going to be the components we're using. And then the second part is how you design with them. This is a link to the, online inventory. This is mostly migrated. There's still some work to do. This is a link to the project where we manage it. But these are links to most of the components we're using with the information on them. In this class, I talk about how these components work. Right now, I'm not going to do that. But I'm going to zip through. Now, this quick tour will take about half an hour. You won't be a master of electronic components in half an hour. This is just to start to orient you. So first off is just ribbon cable. So these ribbons we use, and we use them for a couple of reasons. One is you can connect to multiple ribbons together if you need to send multiple signals. The other reason we use this is rather than having multiple reels of wire, you can peel these apart. So if you need 1 or 2 or however many wires you need, you can just peel off strands of this. They're specified by what's called the AWG. The AWG is the diameter. and then the diameter is related to the maximum current. So if you look at AWG wire current, you'll find lots of versions of tables that tell you how much current you can use for a given AWG wire. So that's a wire we use. Then we use these what are called IDC connectors. And so the connector has sharp fingers. And when you want to put the connector on the ribbon cable, rather than making each joint separately, you push the connector on the cable and squeeze it together. And so it's a handy way to terminate them. There's just one note on that, which is you have the core of the wire in its jacket, and then what comes in is this tooth that pushes into it. If this doesn't come all the way to the bottom, it doesn't make good contact. So if you lightly squeeze it, you don't get a good electrical contact. You need to squeeze it together. We do it by putting it in a vise and squishing it. In production, there's special tools for it, but we use just a vise to clamp it. And so you can use that to put a connector. And so when you want to have a removable connection to a board, that's a common way we do it. For this week, a good thing to do is to add a button. So this is an example of a button. You draw it like this in a schematic. And if you look on the back of that part, there's two bands. And so it has pads on both sides. Electrically, the switch goes between it. So you solder all four of them down, but you can connect signals to either one. So it's normally open, and then when you push the button, it's closed. And then that's compared to a switch. And so this switch, and again, these are all surface mount components. This switch you'll see has 3 leads. And so electrically, it looks like this, where the switch can be in either of these positions. And so physically, you go to the center connection, and then the switch can either go out this way or go out that way. And so the button releases when you let go, the switches stay in the position you leave it in. And we have lots of uses of these to send signals, to control states, to turn power on and off, for example. Ricardo's noting about kits. Ricardo, this is something we're working on. We're looking at putting together a supply chain to source these components. It's something we'd like to do. Okay, resistors. Here's a resistor. The resistor in the US, you draw it like that. Typically in Europe, you draw it like that. And it resists current. So I equals V over R. I is the current flowing through the resistor. V is the voltage drop across the resistor, and they're related by R, which is the resistance of the resistor. And so it sets a relationship between resistance and current. They come in different size packages. We're using the 1206 package, and the 1206 package is large compared to the smallest size you can get them in, but it's convenient because it's easy to solder by hand. And the other reason we use that package is when you have a pad and the resistor, you can route a trace underneath the resistor and still be able to mill it with a 1/64 inch end mill. And so it's a little bit bigger than the densest boards, but that makes it convenient for routing, which we'll talk about. Okay, this is a capacitor. And a capacitor you draw like this. And for a capacitor there, you'll see C is Q over V. So V is the voltage drop across the capacitor. The capacitor stores charge. So Q is the charge on the capacitor. And then C is the capacitance. So capacitors store charge. If I move this over here, CV equals Q. Or to do a little bit of math, dV dt is the rate the voltage changes, and the rate Q charge changes is the current. So in the resistor, voltage is proportional to current. In a capacitor, voltage is proportional to the rate that current is changing. And so we use capacitors to store and filter charge. Now that's a tiny capacitor. A typical value for these little capacitors is micro or picofarads. So a millionth of a farad is the unit. On the other hand, this is what's called a supercapacitor. And until recently, this was crazy, this number. This is 10 farads. So it's 10 million times more capacitance. It stores much more charge. And so you can think about this sort of as an easily charged battery. It doesn't store as much charge as a lithium battery, but it stores it in a lithium battery. That's electrochemistry, moving ions. These supercapacitors are kind of in between. They store much more charge in an electric field. And so you can use them when you need to quickly charge something that doesn't need as much storage as a kind of intermediate sort of battery. Crystals and resonators are used to tell time. And you probably won't ever see one. They used to be important. Processors used to need those. And so we would add those to circuits. At this point, the processors you're using have good timekeeping built in. So you probably won't see crystals or resonators. Now, big capacitors can be very, very dangerous. So power supply capacitors can store, we'll talk about this when we get to output devices, can store large amounts of charge that's hazardous. The little surface mount components we're talking about aren't. When we get to output devices, I'll talk about electrical safety. Likewise, this is an inductor. So let's see, a crystal, you draw like this, and it's a capacitor. It electrically acts like a capacitor, but what's actually in the crystal is a piezoelectric beam. The beam turns voltage into mechanical displacement, and it actually flexes. And so the beam can oscillate back and forth. And so voltage turns into motion, and motion turns back into voltage. And it's designed to resonate like a tuning fork. And so at the right frequency, it resonates, and that gives you a very precise time standard. Inductors, you probably won't see them. You draw them like this. And a magnetic field goes through them. And in an inductor, the voltage across them is the inductance times the rate of change of the current. So the opposite of the capacitor. We use those typically in filters. You probably won't need one. Diodes, you'll certainly see. So a diode, you draw like this. There's two sides, an anode and a cathode. And you can remember that just in alphabetical order. So current goes through a diode. If you look at the voltage across it versus the current, in an ideal diode, it looks like this. In a real diode, it's slightly different. It looks about like that. But what it means is in one direction, current flows easily, but it can't go in the opposite direction. And so one of the main use of the diode is just if you put current backwards into a circuit, you'll kill it typically. And so you use the diode to make sure it can only go in one direction. A very important type of diode is a light emitting diode. So you draw this with a line coming out of that. And when current goes through the diode, light comes out. And so that we're going to use lots of LEDs. Now, an issue with the LED is once the diode has turned on, and this is called the diode drop, and sort of 0.6 is a typical voltage. Once it turns on, there's essentially no resistance. It's a perfect conductor. So if you connect a power supply to a light emitting diode like this, if this is a hefty power supply, your diode literally will explode. And I don't recommend doing this. Early in life, I did this once. You can actually draw so much current, it heats up and you actually explode the diode. So the way you handle that is with something we just covered. You have a current limiting resistor. So always with a light emitting diode, there's a resistor and the resistor sets the current. And so if this is, say, a 5-volt supply, and this is a 1K resistor, meaning 1,000 ohms, which you draw like that. That means ignoring the drop across the diode, it means you get 5 milliamps through the diode. And any LED is specified by the current it can handle, as well as the wavelength of the light. And there's a few other related specifications. And so this one can go up to 20 milliamps. That's a small signal diode that makes a little blinky light. You can have much bigger LEDs that can take amps to light a room. So we'll use LEDs like this to make blinking lights. And sometimes we'll use Zener diodes. These are special diodes that look like this. And in the current voltage curve, if you take the normal current voltage curve, there's in the opposite direction, there's a sharp voltage where it suddenly drops. Why that is subtle. That has to do with interesting quantum mechanics. But we use these to clamp voltages when you need to force a voltage to be clamped at a particular value. Transistors are going to be very important. There's two kinds, only one of which we'll use.
Sorry, could you expand on the Zener diode? On what's the use case?
Okay, the use case for the Zener diode is clamping a voltage. So if you have, if you have a 5-volt signal going into a processor that can only handle, most of our newer processors can't handle 5-volt signals. They can only handle 3-volt signals. So you don't want to put a 5-volt signal into a 3-volt processor. There's a few ways to do the level shifting, but one way to do it is to have a Zener pointing backwards and then a current limiting resistor on this line. And so when 5 volts comes in here, the Zener clamps it down to 3 volts. And so there are other ways to do level shifting, but that's an example to clip a line so it doesn't go above a value. For transistors, a bipolar transistor you draw like this. And the current going this way is proportional to the current going that way. We don't use them because they continually draw current. Instead, we're going to use what are called MOSFET transistors. And this is one of my favorite parts in the class. This is the size of a rice grain, cost 10, 20 cents in quantity. And that little teeny part can switch 30 volts at one, and it can switch 1.7 amps. And that's enough for some of the biggest machines in your lab. So a MOSFET transistor, you can draw like this. There's a gate, a source, and a drain. And you can think about this as it's sort of like a variable resistor where the resistance is set by this voltage. But typically we use it either all the way off or all the way on. If you open the data sheet for the transistor, you'll see a family of curves that look like this. So this number is the voltage on the gate. And you see, once we get up to about 5 volts, it's on. Linear here means that it's acting like a resistor, but the resistance is very low. Gate source drain is like base collector emitter. That's exactly right. So what's different about the MOSFET, so the slope of this curve you can think of as the resistance, and it gets very low. So a key specification for the MOSFET is RDS, which is the resistance between the drain and the source. And a typical RDS is measured in milliohms, in a thousandths of an ohm. So what's going on in the MOSFET internally is there's a semiconductor, there's an insulator, and then the gate is a metal electrode. And the gate induces charge carriers, but it's not actually, there's not really current flowing, it's just setting a voltage. So the voltage on the gate sets the resistance. And typically we use these either all the way off or all the way on. So when the voltage here is 0, no current can flow. When the voltage is high enough, and that depends on the MOSFET, but when the voltage is high enough, then it's an almost perfect conductor. And so we use MOSFETs to switch currents. And so we're going to see lots of examples of that. Let's see, my browser is, okay, I don't know what was just happening. Let me close these tabs. The browser is not paying attention to me. Firefox shouldn't go crazy. I'm going to stop sharing. I'm going to close that and restart the browser. I don't know what just happened. Okay, so let's see, we should be back into electronics design, and then let's get back into here. And hopefully this is working. Good. Okay. There's a question about why use a zener and a resistor instead of a regulator. It's different time scales. The zener switches quickly, but it dissipates through the resistor. The regulator is more efficient, but runs on a much slower time scale. And I'll talk about regulators in just a minute. The difference in logic level MOSFETs and non-logic levels is just the gate voltage, that the logic level MOSFETs switch at a much lower voltage. It used to be you needed maybe 15 volts for a MOSFET. Logic level ones switch at 5, and some even go down to 3. Now, there's 2 types of MOSFETs. This is an N MOSFET. This is a P MOSFET. N MOSFETs you use on the low side. So you have your load, and this goes to the supply. P MOSFETs are the opposite. You use them on the high side, and then your load is down here. So an N MOSFET is a sink of current. A P MOSFET is a source of current. And again, for this class, I'll just say it. In these notes, I explain why that's so. I'll just say it. And so this might be, say, 42 volts on a powerful machine. This is 0, and we might need 5 volts here to switch that. So you switch on the low side. The P MOSFET, if this is 42 volts and you need 5 volts to switch it, it means you need to switch it. This needs to be 37 volts, a high voltage. And so when we get to power electronics, we'll talk about how you make the high voltages to switch P MOSFETs, but we'll need them. For example, an N MOSFET can make a motor spin in only one direction. If you want the motor to spin in both directions, you need a P MOSFET. And so we'll talk all about that in Output Week. But we use the MOSFETs to switch currents. Then this is a regulator. Loading slowly from DigiKey. I wonder if that was the problem. Okay, so this is the regulator. This takes anything up to 30 volts, and in this case, puts out 5 volts. So many of the processors we're using want 3.3 volts in. USB gives you 5 volts. So you go through a regulator, and then on this side, you get 3.3 volts. Regulators always need a capacitor here. The reason is they're running a control loop. And to be able to run the control loop, you need to do that feedback. It helps to put a capacitor here. This one stores extra charge. This one is optional depending on the application. This one is essential. Now, the regulator on this side is specified. So the one I just showed you goes up to 30 volts. To regulate, you can't put in 3 volts in and 3 volts out. You need a little bit of room above that. But a typical use for this would be, say, USB, or this might be 9 volts from a battery. And then the regulator lets you power it. Now, we'll talk more about this in Power Week. Power, meaning how long your battery lasts or how hot the circuit gets, equals current times voltage. And so the current through the regulator times the voltage drop across it tells you how hot the regulator gets. And so if you need a lot of current, you need a bigger regulator. And eventually you need there's a more efficient thing than regulators that are called buck and boost converters. But for our purposes, we'll just be using these regulators. Now, the Zehners I mentioned switch quickly, but they always dissipate power in the resistor. The regulators are more efficient, but they operate on a very slow time scale. Those are just for the DC signals. And so you'll see lots of use of regulators going into, let's see, if we go here, schedule, one of our processors we like is the SAMD11. And so this is this speaks USB. And if you look at the circuit, the USB comes in, and here's a regulator with its capacitor that's making 3 volts from the 5 volts of the USB. Op amps, sadly, you'll never see. This is a beautiful part that you'll likely never see. It amplifies the difference between 2 signals coming in by a huge amount with very low noise. And then the way you use these is you make feedback networks around them. And so a typical one looks like this. And so we use these to amplify signals. And the reason I say you probably won't ever see one is the processors we're using have amplifiers for low-level signals built into them. And for high-level signals, we'll use power transistors. And so you probably won't see those. Then we already met microcontrollers in the introduction to embedded. This is a classic one we're using. There are various reasons to use the ARM parts, the AVR parts, the SHAOs, the ESPs. And then we have 2 classes coming up. This class is on inputs. So I show examples of reading switches, magnetic fields, material properties, temperature, light, motion, distance, acceleration, sound. And so lots of examples of sensors. And then this example is producing, this week is outputs. So I'll talk about LEDs that make multiple colors, arrays of LEDs, various sorts of displays, driving speakers. A lot of time we'll talk about making all sorts of different motors move. And then one final note for the week is in networking week, I'm going to talk about taking a note from my notes. I'm going to talk about protocols. So in addition to USB, one is called SPI, one is called I2C. These are to talk to various sorts of peripherals. And so if we go back to Adrian and his Adrianino, he has on here, he's bringing out the signals for I2C. He's bringing out communication signals. If we take let's see, this one brings out USB. And so he's taking various of these protocols we'll be learning about and bringing them out to connectors you can connect to. Just in terminology, there's a question about IC versus MCU. When I say MCU, I just mean a microcontroller, and a microcontroller is a type of IC. So analog, digital, all the parts all the things that have a chip in a package bonded to leads are integrated circuits. And a particular type of integrated circuit is an MCU, which is just one shorthand way to say microcontroller. Okay, so those are a basic set of components. And so just to start this week, a good thing to do would be if you take your processor of choice, it could be any of them, you could add a button so you connect it with a pin to ground. You could add an LED with the resistor going to ground. You could also make connections out to USB. You could make a connection out to I2C. If you want to make audio, you could make an I2S connection if you have a processor that does that. These are some of the things that you could add to the processor you're using. Now I'm going to talk about circuits. So these are dear colleagues. This is a Bible of electronics. You should all have this book in your lab by your electronics workbench. I can't recommend it strongly enough. So you're going to design circuits. First, just a couple notes on circuits. When you have a complex circuit, all of the voltages around it have to add up to 0. And in a circuit, all the voltages in and out of a node have to add up to 0 as one thing, principle. That's called Kirchhoff's laws. That's almost always true. Here's what I mentioned a moment ago, which is power equals I squared R, and it also equals IV. And so if you have a resistor and current goes through it, power goes as the square of the current. If you have, for example, a regulator and current goes through it, power goes as the voltage drop across it. This may sound abstract, but this is how long your battery lasts before you have to replace it. Or for example, if you're doing power electronics, this is how hot the part gets. And eventually, even though the transistors we're using have very low resistance, when you drive big motors, you can pull so much current through them that just getting the heat out of them is a problem. And so if you look at a motor controller heat sink, you'll find in motor control circuits fins on the board like these, whose job is just to help get heat out of it so it doesn't overheat. And if it overheats, eventually it shuts down or fails. So power is a really important concern. EDA is what we're doing this week, electronic design automation. You're going to make drawings. So for this, let's go back to, if we take embedded programming, any of these examples, you're going to make traces that you're going to produce in 2 weeks. So you're going to make a drawing. You could use any drawing tool, but you probably shouldn't. So EDA, it has to be hierarchical because you're going to have, for example, a wire thickness, and you want that to be a global parameter. You're going to have a component, and you want to be able to reuse that in multiple places. A big part of EDA is packages and footprints. So let's go to Octopart. This is an older part, but I'm just picking it as an example. This is the same chip. This one is a surface mount package. This is what's called chip scale packaging, where it's a much tinier one. And then this is a dip package, those with leads that go through. So the same part is available in multiple packages. For each package, there's a footprint, which tells you the shape of the leads to connect to it. And so we need libraries for the packages and footprints. So there's a workflow where you enter a schematic, which is the logical design, but that doesn't tell you where the components go. Then you have to physically place the components for where they go on the board. So once we're done, let's see, if we go back to the Adrianino, once you have the schematic, then here's the layout, and he had to design where each of these parts go. Once you place the part, you then need to route it. Route it is figuring out where the leads go. Once you've routed it, for a complex board, before you make it, you simulate it, and then you produce it. So those are all the steps. And one of the most non-trivial ones you're going to spend a lot of time on is routing, figuring out how to get all the leads to their destinations. Then for each process to make the board, there are design rules. So the design rules include issues like how skinny can a wire be before it fails? Another one is how close can two wires be before they touch? And the design rules depend on the process. So we're milling traces, they can't be any closer than the milling bit. Typically, we've been using 1/64 or 15 thousandths of an inch. For a commercial board house, they're 5 thousandths of an inch is a design rule. We'll talk more about this in electronic production. For state-of-the-art microfabrication, they go down to millionths of a meter. So now for routing, in electronics production, we're going to talk about layers. So let me show these examples. This is a one-layer board. All the traces fit on one side. So that's easy to make because you only make it on one side. If you look at this board, there was a problem. I couldn't get this trace over to where it needs to get to. So the 0 here means I'm using a 0 ohm resistor just to jump over. I'm hopping over a trace with a jumper, meaning it's a resistor that's 0 resistance. And so I'm calling that 1.5D because it's 1D, but with some crossovers. This is a 2D board. In this case, I'm using vias. I'm making a hole from the top to the bottom, and then I'm routing on both sides of the board. And when boards begin to get more complex, you need 2 sides to route it. And then beyond that, 4 is common, where you have signal on the bottom, signal on the top, and you have power and ground inside. And a really dense board, like say your computer, might have a 10-layer board. So for this week, you'll be using either 1 or 2-layer boards. 1 is less work for you to make. 2 is a little bit more convenient for the routing. So how do we design the board? You could just draw it. So this was a student who was a good artist. And what he did after doing the assignment was just by eye, he was a good enough artist. He looked at the components and he made a drawing of what he thought the footprint was. He scanned it in and he produced it. Very expressive, no software needed. You can't edit it. You need to be a good artist. And yes, you can't modify the drawing. So that's an extreme. Years ago, when I first learned to do this, we would do it with tape. We would have drafting tape. You would tape, and then we would have stickers you would put down for the footprints, and then you take a picture of it to make it. Again, that's no longer done. Then these, so Tinkercad, virtual breadboard, fritzing, all of these are great beginner tools. So what they let you do is, in a graphical way, assemble your components and model what they're going to do, simulate it. And so these are very friendly for tinkering, for learning what the components do. However, the limitation with them is they're limited. they don't have the power of the tools I'm going to describe. So there's a limit to the complexity of what you can do with them. Then these are beginner-friendly tools. There are a number of these emerging. This is another family of tools emerging. These are all options, but I would focus on, for today, KiCAD, Eagle, and SVG PCB. So I'm going to spend more time on KiCAD. KiCAD. So question? Yeah, Tom's noting Tinkercad keeps getting better. The boundary is moving. You're right to keep adding to it. So KiCAD, it is not from CERN, the particle accelerator, but it's overlaps closely with CERN. KiCAD is freely available, open source, cross-platform, and very powerful. So strong endorsement for KiCAD. So it's actually a series of programs that are connected, and they've improved the connections over time. So I've started up KiCAD. You need to tell it the libraries to use. And so we have a library of the parts in the Fab inventory, and Chris on this call has done a lot of work on that. So I need to tell it to use my libraries. It has ones built in, but there's a Fab library for parts we particularly use. So now I'm going to start a project. So I'm doing a new project, a demo, and it just made templates for me of the schematic and the PCB. The schematic is the design, the PCB is the layout. So I'm now in the schematic editor. I'm going to start adding components. So this is all of the parts it knows about. And so I'm going to reach in, I'm going to pick out a processor, and then add that to it. So there's my processor. Now, what I added doesn't look like it physically. It's a conceptual representation of it. And just for this example, I'm going to add a resistor. So I'm going to do something sort of nonsensical. I'm just going to connect a resistor to two pads, which normally there wouldn't be a need for that, but it's just to demonstrate making a circuit. So there's my resistor. I've placed it. Now I need to connect it. And I'm drawing lines, but the lines are more than lines. They're logical connections. So I'm making logical connections between the pads. Okay, so I just added a processor and a resistor. Okay. Now what I need to do is I have to tell it the footprints. These parts come in many different sizes and shapes. So now what I'm doing is I'm going into an editor and I'm picking what footprints to use for these, the shape of them. Okay, now I'm just switching modes. Now I'm going to the PCB design tool. So in the PCB design tool, now I have to figure out what goes where. Okay, so it just brought in, let's see, CODAD does KiCAD. Okay, good. The answer already is Fab library has the RP2040. So now I've got my two footprints of the parts ready. And then you'll see these skinny lines. These are called air wires or rat's nest. Those tell me logically those are connected. So now the next thing I'm going to do is I'm moving the resistor and I'm picking where I'm going to put it. And then in this simple example, you see those wires are crossing. So I want to flip the resistor. So I'll flip the resistor. And so now it's near the part and I flipped it so things are on the right size. Now I need to route. And so route is turning those logical connections into traces. And so this is what we're actually going to produce. And then once I get them connected, the air wire disappears, the rat's nest goes away, and it tells me it's connected. So now this is a trivial example, but I routed those wires. Then this doesn't tell me the board size. So now I'm going to make, on the right are all these different layers. There's copper on the top, there's copper on the bottom. Right now I'm going to work on a mechanical layer, which sets the shape of the board. And then here's a neat thing. Right away, while I've been doing this, all of these have 3D design, 3D descriptions. And so KiCAD already can give me a 3D render of my design. And I could export that right away into my CAD environment to design CAD around my design. So I made the schematic, I picked the footprints, I brought it into the PCB tool, I routed it, which was easy for this example. And then I've already got a 3D design for my CAD. And then the last thing I need to do is I need to export it to produce. So commercial board houses almost always take Gerber, an ancient format. And so you run a CAM job to export it. But here what I'm going to do is, because we're going to do in-house where we want an SVG or a PCB typically. In a moment, you'll see why. I'm going to make an outline on this layer that I'm going to use for the export on another layer. Then I'm going to ask to produce SVG. And then in mods, if you're using that, I'm going to bring in the traces. And so now I can machine the traces exported from KiCAD. And then I'm going to bring in the interior I brought in, and I'm going to mill around that to mill out the board. Yeah, Chris is noting not all the parts in Fab Lab have 3D designs and inviting that. So yeah, there were a question about corners. When you commercially produce a PCB, you'll often see, like in the example I did, corners that look like that or corners that look like that. The reason is just that when you do chemical etching, in the vicinity of a sharp corner, the chemical etch rate is different than in the middle of the line. And so but by stretching them out, one reason is just when you're pushing the resolution, the etch rate is similar. It's just simply that. You'll also sometimes see these in very high frequency circuits because how a signal propagates depends on the shape. But most commonly, it's avoided just for etching. But that only matters when you're pushing the limits of the design rules. For what we're doing, it doesn't matter. And so you'll see I have lots of sharp corners in my designs. Okay, so that was in KiCAD. The one thing I didn't show is, oh, and in fact, I need to add something to this page, which is the DRC. So a DRC is a design rule check. And this is where, when you produce it, you can study your design to ask, is everything manufacturable? But you can tell it what are the limits of your process, and it'll go and do that check for you. And a classic version is, let's say, here's your processor, and you bring a lead out, and you bring this lead out, and say this one is going over here, and this one's going there. If you make these too close together, when you try to make it, these will be touching, the end mill can't get in, and this whole thing will be a solid block of copper. So the design rule checks that. Yeah, and KiCAD also does ERC, which is electrical rule checking, which is just checking the basic connectivity in it. So KiCAD knows how to do all of that. Ricardo's sending me a note about pull up, pull down resistors. The when you have a switch like this going to ground, when the switch is open, when the switch is closed, this is 0. But when the switch is open, you don't know what the voltage is here because nothing is connected to it. So you handle that by putting a pull-up resistor going to the switch, like 1K is typical. However, you don't need that for the switch, because inside you can turn on a pull-up resistor on the processors. Another place where you'll see this is when we go to power transistors. I'll talk about this. Here's our load. Here's ground. You'll see me put a resistor here. This is a pull down resistor. That's because until you program the chip, you don't know the voltage going to this, and you can fry your load. And so this resistor keeps the transistor off until the power turns it on. Yeah, so I forgot, I'll add a note to this page about DRCs and ERCs. And so KiCAD lets you check that you've got all the wiring done and check that it's manufacturable before you go to fabrication. KiCAD also has a nice tool that lets you manage the bill of materials from your design. So KiCAD is open source, cross-platform, freely available, very powerful. Biggest limitation was it's a series of separate programs, but those have gotten much more closely connected. So KiCAD's lovely. Eagle has an interesting history. Eagle started as a commercial software, became open, was bought by an electronics vendor to get you to buy electronics, didn't quite work out, was then acquired by Autodesk, is now built into Fusion. So Fusion commercial is expensive, non-trivial, but they have affordable pricing for things like maker nonprofit use. And in particular, they're very generous in providing access for Fab Labs, Fab classes. So if you're using Fusion, what's great about Eagle is now completely built into Fusion. So you don't need to switch between CAD and EDA. You can design your circuit board right in the same environment as the rest of the project, and they all talk to each other. So changes in the PCB immediately appear as changes in the CAD. And so that's the great strength of Eagle plus Fusion. A nice thing about Eagle is everything you do in Eagle appears as scriptable commands. And so there's a very, KiCAD is extensible. Eagle is really, really easy to script the way it's designed. I'd say the main downsides to Eagle and Fusion, one is by merging it with Fusion, it's made it a little bit harder for a traditional electronic designer to use. But in return for that, for a non-traditional electronics designer, it's made it more accessible. To use it, you need to be connected to the Autodesk cloud. You need an identity. You need one of the terms with Autodesk to be able to use it. There's notes in the chat that there's a number of deals for some startups, for individual things like that. Tom's noting good support for the libraries. So as long as you're comfortable being in the Autodesk cloud for Fusion, then Eagle is a great choice. KiCAD, you don't need to pay anybody and you don't need to be connected to anything. You can just use it, but it'll export to CAD, but using it and doing the rest of CAD are separate steps. Now, libraries, here the story has gotten much better. So this is a link in Fab Cloud to various versions of these libraries. And in particular, Chris has been very active and invites you to join him in keeping current the KiCAD library. The other good news is these are all a bunch of examples. So DigiKey provides KiCAD libraries for almost all of its parts. And then these are a number of platforms like these are meta librarians. These are librarians that support multiple kinds of parts for multiple kinds of design tools. So these are so well supported because the people who sell the parts want you to be able to design with them. So you can learn to make footprints from scratch, but typically whenever you find a new part, somebody somewhere, the vendor or a maker has already done it. And so these are all ways to share librarians. And so it's an interesting skill to learn to make footprints from scratch, but you may never need to do it. And in particular, there are links to the Fab libraries we're using. Oh, Ricardo's noting DigiKey hasn't been updated. I'm sorry to hear that they were keeping that more current. Now, before we go on, one final note on auto routing. Auto routing is where you just push a button and ask it to route. You need that on really, really complex boards, but auto routing is a hard math problem. And typically it'll do much worse than you on these smaller boards. So the auto router will end up with like lots of vias and complex routes. And so routing is like solving a puzzle. Some people hate it. Many people, including me, and likely many of you, will find it's actually a fun puzzle. That when you're in the wrong mood, it's irritating, but when you're in the right mood, it's a really fun challenge. And when it's really satisfying when you find a good routing. But it's not a trivial thing. You have to think about all the different ways to arrange your components and the ways to send the leads to get them with the smallest number of vias or crossovers to make a nice, compact, nicely laid out board. These are more advanced tools. These are industrial strength tools to simulate. All of these do simulation from the physics. One I'd mention just to start is Falstad, is a really neat one that runs in a browser and has all sorts of, like this is a Delta Sigma ADC, and you can edit these right in the browser and then run a mixed digital and analog simulation. So this is a fun tool to play with it. And again, the more beginner oriented tools I showed you all do simulation right from the outset. Let's see, there's a note about deep PCB. Interesting. I mean, some background to that is I have a visitor in my lab who many years ago wrote a classic paper where he introduced what's called simulated annealing, which is one of the most important techniques for optimization. These are at the foundations of what grew into AI, and he did that for routing PCBs. He invented it to route PCBs at IBM. Okay, last two topics. When you make really complex circuits, like a billion transistor integrated circuit, you don't draw a schematic, you use a hardware description language. And so for many years, when you look at my examples, let's go back to just embedded programming. If we take any of these, all of these, if look like this. And so what's going on there is I'm in an editor here, and I'm making, and then here's a render, and then I've got a solver there. And what I'm doing is I'm making a hardware description language. So rather than clicking and drawing, I'm essentially programming. And so right now I'm showing that from this environment, with this hardware description language, I can make all the layers of the design. And now I'm going to go back and I'm going to do some editing. And so I'm going to add a resistor, and then I'm going to wire to it. But instead of clicking and dragging, if you look at what I'm writing, I'm describing, I'm saying this resistor lines up with the crystal and the connector, and then it connects to these pads. And so I'm narrating how I think about the design, and then it's rendering that. And that's not at all familiar. That's not recommended for beginners. But I've done this for so long that rather than sort of doing it by motor control, this lets me describe how I think about the design. And so that turned into this project, SVG PCB. So Leo and Quentin wrote this inspired by what I showed you. They took all of my example circuits and brought them into here. And so let's see, if we take this one, here I'm now in SVG PCB. Here, I'm going to make the rearrange the window. And so what's going on here is, here's my design. In this window, I can move things around. But when I move them around, I'm changing numbers over here. If I come over here, I can, let me move this over. On this side is a hardware description. And so I can edit the hardware description. And you'll see when I move this component, I'm moving everything connected to it there. If I come over here, if I move it graphically, I change the program. And then if I bring in a component from here to here, I actually modify the program over here. And so in this environment, I can draw graphically and get a hardware description, or I can do the hardware description and draw graphically. And what I just showed, where one component moved a whole set connected to it, is in this program description, you can have all sorts of complex relationships with parts that are hard to do graphically. And I just realized there's a link. I think I have this on, yes. I'll put this in the chat. Oh, sorry, I just sent that to Ricardo. Let me send this to everyone. This is a link to this paper that talks about SVG PCB. Now, SVG PCB isn't standard. It's not a conventional way to design PCBs. On the other hand, it's both in some ways much easier, but in some ways much more powerful because it links the graphical with this programmatic representation. And so I do recommend learning about KiCAD and Eagle, one of those, because those are a more standard way to do it. But this is an interesting emerging way to do it. And you could do everything in this class happily with it. Saturdays we'll talk more about it. Jason asked ChatGPT for a schematic. How did it do, Jason?
Sorry, I never know where I put my mute button. It made some sense, sorta. I'm not familiar with KiCAD yet, and I was hoping to use it as a stepping stone, but it basically output a code box and then just said repeated connection tilde 3300 2700 a bunch of times, which sounds like a key matrix to me, but I don't know anything.
Okay, you can try opening it in KiCAD. Hard to tell from that. Okay, last topic is in not next week, but the week after, there's going to be a recitation on debugging. And what I've got linked here is this is a power supply that lets you vary voltage and measure current. This is a meter that lets you measure voltages, currents, and resistances. This is a little oscilloscope that lets you see analog and digital signals. This is a handy tool that lets you decode logic signals. Here's a bench version. And so you're going to need all of those to debug. As we start building circuits, there's a really challenging boundary where when something doesn't work, you don't know if it's high-level software, for example, on a desktop computer, if it's low-level software in an embedded processor, or if it's a mistake in the circuit electrically. And so you need these sort of tools to figure out, is it a hardware or software problem and what's going wrong? And they can be very subtle. For example, it can be that when a transistor switches, it draws so much current that there's a spike on the power line, and the spike on the power line resets the processor. And so it looks like there's a logic problem in the processor, but it's actually they're talking through a signal in the power line. So as a group, what I want you to do is take one of the boards from last week and just poke at it with this. Measure how much power it consumes, measure the voltages in the circuit, look at the analog signals, look at the logic signals, decode the digital data, look at how the power line isn't perfect, can be noisy. And so just learn about the signals from an existing board. And then for this week, design a development board. You can start looking to your final project and focus on it, or it can just be a generic one. But at a minimum, add, for example, an LED that you can blink, add a button that you can read. You can add some other ways to communicate. Pick one workflow. Extra credit is try another one. Another nice thing you can do for this week, the point of make a case is to go from EDA to CAD. So export your circuit design into a tool where you can then design the packaging around it. Another extra credit thing is you can take one of these fun tools. You can take the industrial strength tools. You can take these newer sort of ones, and you can simulate what the circuit does. And so at the end of this week, you'll have designed your circuit. And then in 2 weeks, I'm going to talk all about how you produce circuits. And in 2 weeks, you're going to make it. Yeah, Jason is saying, yeah, Jason, I don't mean a conceptual case, I mean a physical case. Meaning, don't argue in a court of law for your design, just make something to package it. Okay, so this was a lot. Okay, Ricardo's asking about, yeah, so Ciudad is, you don't have to make the circuit this week. If you want to get ahead, in 2 weeks, we're going to do electronic production. In 2 weeks, you're going to make what you designed this week. If you're eager, you could make the board, but it's not required. Let's see, Kat, I think, is saying we should make a case for your design. So if you want, you can interpret the extra credit that way and make a case for your design to argue for it. Ricardo's asking an important question about switching. So if we go to electronics design, and then we take the transistors, a key specification is how fast they switch. And let me see if I can pull that up quickly. But the transistors we're using switch depending on the transistor. Okay, good. This is exactly what I want. So right here are the transition times, and you'll see they're measured in nanoseconds. So these switch at nanoseconds very, very quickly. And so we're going to use that to do pulse width modulation. And that's how we're going to vary how bright a light is or how fast a motor turns. And so they switch very quickly. I like the thread in the chat about the alternate meaning of case. So, but by all means, you can interpret case however you want to. Okay, that's electronics design. If you haven't already done it, do make sure you have a tracking page for your final project. If you get excited, you can make the board, but don't really worry about that because in 2 weeks, everybody's going to be doing that. And then no recitation this week, but week after this, Hank will lead all about debugging. Okay, happy electronic designing. And then, sorry, Saturday, open time, we'll spend more time on SVG PCB. Okay, see you all in a week. Bye-bye.
Bye.
Ciao Johnson.
سلامة.
5分钟说一下。拜拜。